Thanks, Dan. Hey, everyone. My name's Oleg. I am a PhD student at the University of Illinois in the nuclear engineering department there. I've worked with both Professor Madikin Monk and Professor Katie Huff. I work on computational methods for neutron transport there. And today I'm going to talk to you about transport independent depletion in OpenMC. You're going to learn what that is as we go on in this presentation. I just want to mention I have another collaborator, Paul Romano, who cannot be here, but he's a staff scientist at Argonne National Lab, and he helped a lot with this work. So you might have heard in the news about this, like advanced reactors, small modular reactors. There's a lot of interest in building these sort of new reactor designs to power things like data centers and AI and all that good stuff. None of those reactors actually exist yet. One of the best tools we have to study these designs is computation. Unfortunately, simulating a nuclear reactor is extremely expensive. We have this 7-dimensional equation called the neutron transport equation that we need to solve. I don't have it shown here. I can show it to you if you want. It's a little scary. We have 3 spatial dimensions, 1 energy dimension, 2 angular dimensions, and 1 temporal dimension. This figure is of the Advanced Test Reactor at Idaho National Lab. If you look at this blue cruciform in the center, that is our fuel. Each one of these segments is split up into plates. Each plate contains the fuel element. The pink circles on the outside are the control drums, and then you have all sorts of ports and holes for different instruments and sensors and stuff like that. This is a very complicated geometry. Most reactors don't look like this, but they have similarly complex geometries. So you have lots and lots of surfaces and regions and things that you have to discretize in your solution method. We have 2 solution methods that we use. We have these like deterministic solution methods like finite element method, finite difference. And then we have the Monte Carlo method where we use random sampling to simulate a neutron bouncing around a reactor. Fun fact about Monte Carlo, it was actually invented by John von Neumann and Stanislaw Ulam in the 40s to simulate this exact process. Now it refers to a more broad term of methods that are used in many different scientific domains. Regardless of the method that we're using, you either need lots of discretization of these complicated geometries, or you need to run lots and lots of particle histories to get pretty good results. To do that, you're going to need a supercomputer if you're doing any large reactor model like this. So this is a very expensive process, and we're always looking for ways to make it cheaper. I want to talk a little bit more about the fundamental physics of what happens inside a nuclear reactor. Katie kind of beat me to the punch here this morning. This is almost the same figure, but we have a neutron on the left in white coming in, hits a uranium nucleus, causing it to split. During that splitting, we release heat, fission products, and additional neutrons. These neutrons can go on to hit other uranium nuclei, further fissioning those, or they can get absorbed by like uranium-238 to produce plutonium, or they can be parasitically absorbed by neutron poisons. We design reactors in such a way that the number of neutrons produced equals the number of neutrons that are consumed. So we have a nice steady state. That is, we would have a steady state if things weren't changing all the time. As uranium splits, it gets sort of burnt up, it gets consumed, and we have these fission products build up. You have other reaction products build up. Some of them are radioactive and they like to decay. They can release neutrons. Some of them are stable and they just sit there and they don't really do anything. But the point is that things are always changing inside a nuclear reactor. Your fuel composition at day 1 is not the same as day 2, day 3, and so on. This process, this sort of changing of the fuel, this is called depletion. This figure on the right shows uranium being spent and plutonium being built up over time. I don't have a figure of radioactive decay, but it would probably look something like that. We care about this because there's a very strong coupling between neutron transport and depletion. We produce things like neutron poisons. Back when they were doing experiments in the 20th century, like on Chicago Pile 1, they would run the reactor and then it would shut down for 3 days and then it would start up again. That's due to neutron poisons. This is like xenon-135, cesium-137, samarium-149. Nowadays, we design reactors a little smarter, so we mitigate these effects, but it's something you need to think about if you're trying to build a new reactor that no one's ever built before. We also care about depletion because as your fissile, the atoms that can fission change, that changes the energy distribution of your fission neutrons. And that affects pretty much everything in your reactor. That affects what reactions are going to happen. So that's a very important quantity to consider as well. Finally, on the sort of tail end of this process, when we take the fuel out of the reactor, the fission products that are decaying continue to do so long after it's removed. They release heat and radiation, and that affects how we handle the fuel. It affects how we store it, and it affects how we can eventually reprocess it. From the computational perspective, depletion makes everything even more expensive. We have to track thousands and thousands of nuclides for any given material that we're simulating. In a reactor, you typically have a non-uniform neutron density, so each fuel element will become its own unique material. You have to track that as well. If you're considering the axial discretization, if you're doing full 3D, neutron density is also non-uniform in that axis as well, so that adds even more orders of magnitude of complexity. On the right here, this is just a web of the kinds of reaction chain that can happen. I'm not going to read off of it, but you can see the complexity here, and these are all things that can happen, and this happens all throughout the periodic table. Okay, so we've talked about depletion, we've talked about how hard it is to simulate reactors. Let's actually look at some of the methods we use to simulate depletion. This is the governing equation for nuclide depletion. We have the change of nuclide density of nuclide I with respect to time on the left, and then on the right side we have these four terms. We have two production terms, two consumption terms. We have production of I from a nuclear transmutation reaction with J, and then if J is a radioactive element, it can decay into I, potentially. We also have the consumption of I in a nuclear transmutation reaction, and then we have decay of I if it's unstable. I want to point out two of the terms in this equation. This little sigma I, that is what we call the cross-section. The cross-section is a target area for a reaction. The larger it is, the easier it's going to be for a neutron to hit it. It's dependent on energy, so depending on what energy the incident neutron is coming at, it'll see a different target area. This phi term, this is the neutron flux. This is just a measure of the neutron density in the reactor. It's neutron density times the velocity of the neutron. And then we also have F and lambda. Those are the yields and decay constants. We actually need software to run this equation in to solve it. There's lots of different options out there. I'm a big fan of OpenMC. OpenMC is a Monte Carlo neutron particle transport code developed initially at MIT and is now maintained by a group at Argonne National Lab, including one of my collaborators, Paul Romano. But it has a community of contributors all over the world. It's open source. Every feature in there is developed by the community. It has a C++ core for the neutron transport side, and then a pretty feature-rich Python API for creating input, processing your output, and this Python API also contains the depletion module. A lot of the Python API, including the depletion module, leans very heavily on the infrastructure of the scientific Python community. Some examples are NumPy for array handling, H5Py for output file processing, Matplotlib for the plotting functionality, SciPy for sparse matrices, which is actually very frequently used in the depletion module, and uncertainties for uncertainty propagation. So I want to talk a little bit more about the specifics of how we would run a depletion simulation. We need an initial value for n, the nuclide density. This is given by the user's input and the problem's initial conditions. You could have a pressurized water reactor using 5% enriched fuel. Your things like your cross-section, your reaction yield, and your decay constants, those come from material properties that are provided by data libraries. This data is loaded into memory for speed because there's a lot of it. And then for the flux, unless you're using a very simple geometry and you can get an analytic solution, you have to run a transport simulation. There's also this time variable. We don't directly solve the neutron transport equation in time, but we do sort of update the material composition at each time step during a depletion simulation. Internally, these time steppers are called integrators. They range from simple Euler method to more exotic and complicated methods using like stochastic sampling. It's pretty impressive what's in there. This is a simplified algorithm of OpenMC depletion. So first we run a simulation using our initial conditions and our data to obtain a solution for the flux. Then we plug in that flux and all of our data into equation 1 to get those production and consumption terms. We solve equation 1 using this method called CRAM, Chebyshev Rational Approximation Method. I'm not going to talk about that any further, but there's a citation there if you want. It's its own topic that deserves its own talk. And then we update the material compositions in the input file, and we rerun this process for as many time steps as the user has defined. And we get a nice time series of how our nuclide compositions are changing over time. Now, I've talked a lot about how expensive this process is. You're probably wondering, how do we make this cheaper? Because the title of the topic is Burning Fuel for Cheap. Well, let me tell you. There's two things that we do. One is that we assume our fluxes are static, so we're decoupling transport from depletion. Second is that we use a discrete energy grid to transform the integrals in equation 1 to sums over energy groups G. This makes it a lot simpler and faster to evaluate. We just have to do a NumPy product as opposed to sampling each individual reaction. We built up some infrastructure in OpenMC to support this. First, we have this microXS class. This is just a container to store energy discretized cross-sections indexed by nuclide, reaction, and your energy group. My collaborator Paul Romano created this very handy get microXS and flux function to run an OpenMC simulation that just pops out your energy discretized flux and energy discretized cross-sections for all the nuclides in that model. You can define this pair for as many materials or domains as you want, so you can get as complex as you want with it. And then we have the independent operator class. This is a drop-in replacement for the class that is responsible for step 2 in our algorithm. Rather than running an OpenMC simulation, we just solve equation 2 because we have all the data we need immediately. To test this feature, we used a model problem of a PWR pin cell. This is shown on the right. The blue square is the water. This black ring is the cladding. That's just a piece of metal that contains the fuel pellet, and then the pink is our fuel. We use 4.25% enriched fuel. It's pretty close to what you'd find in an actual reactor, and then reflective boundary conditions to approximate what we would see at the center of a reactor. We ran 3 cases. Our base truth is normal transport coupled depletion in OpenMC. Then our feature, case 2, transport independent depletion. Then as a sort of sanity check, we recoupled case 2 to the transport by doing a transport independent depletion simulation, but with recalculating those cross sections and fluxes at each time step. This is just a sanity check to make sure we're not doing anything incorrect. This should be more accurate than case 2, but slightly less accurate than case 1. Each case we ran for 10 time steps with 2 different time step sizes. We had a 3-day time step for the xenon 135 poisoning limit I talked about, and then a 30-day time step to sort of see, okay, how good is this when we really decouple the transport from the depletion? This might be something you find in certain domains in the space. I can talk about that more at the end if people are interested. For our energy grid, which we refer to as energy groups in nuclear engineering, we used a single energy group. We had an 8-group structure and then a 40-group structure. Generally, the more groups you have, the better resolution you have in energy. So this is seeing how that affects the simulation results. All right, let's see how we did. So I don't have explicit runtime data, unfortunately, but based on file timestamps, I can sort of estimate how long each run took. As expected, case 1 took several hours on a cluster. Case 2, very, very fast, minutes to seconds, like night and day, extremely, extremely fast. Obviously, this doesn't include the initial simulation to obtain your flux and your cross sections, but I'm assuming that's a fixed cost. Once you have those, you can reuse those for the model for whatever time step size you want, whatever simulation you want to look at. And case 3, similar runtime scale to case 1. It was actually longer though, because each time we had to rerun an OpenMC simulation, we had to reload all of the data back in, and that can take quite a while. So yeah, case 2, very fast. That doesn't do us any good if it's not accurate though. So these 2 figures show the relative error of case 1, of case 2 on the left and case 3 on the right, relative to case 1. So these relative errors are all relative to case 1. I want to point out the scales on the x-axis here. Case 3 is quite low. We're less than 1% error, so pretty close to what the results for transport coupled depletion are. Then on the left, we have like 15, 16% at the top errors. So not great, not terrible. Let's zoom on this a little bit more. So we see how uranium is very, very low error. Like it doesn't even show up on the plot. So that's nice to see. We then look at neptunium, plutonium. Those are all less than 5%, so that's acceptable. Then we see this jump in error. We're up past 5%, 6%, 8%, 10%, 15%. These nuclides are all present in trace amounts in the fuel. They are not produced very often, and when they are produced, they're produced in very low amounts. So our hypothesis is that these nuclides are just off from what they should be because of the low amounts that they have. I do want to mention we are looking at actinides here. Actinides are interesting because they are the elements, uranium and everything around uranium. These are what drive nuclear chain reactions. So that's why we care about these. If we go to the 30-day time step, we see similar magnitudes of errors, but we see different dynamics. Before we had a pretty constant under prediction. Maybe it got a little worse as time goes on, but not by a very large amount unless we're looking at the trace elements or trace nuclides. Here we see something different. We see this flipping. So we see an initial under prediction followed by over prediction. At least for case 2. For case 3, doesn't matter. Error is low enough. The reason that this is happening is because we're seeing an well, it really depends on the specific nuclide and reaction we're looking at. For something like plutonium-241, we see it starts under and then it goes up. Most of plutonium-241 is produced from N-gamma reaction with plutonium-240. The reaction rate of plutonium-240 N-gamma is following that same trend. So that sort of explains why we're seeing this flipping. If we go to the fission products, these are all very, very low. Similar setup, relative errors relative to case 1, case 2 on the left, case 3 on the right. We're in like less than 10 or less than 5% error now. The reason for this is large majority of these fission products are being produced from reactions with uranium. Uranium is the primary fuel in the PWR fuel element. So because the uranium error is so low, that sort of propagates to the fission products. So that's why we get very low errors here. And this is for 3 days. For 30 days, we see similar things. Error is extremely low. I would say it's acceptable. For the 8 and 40 group cases, we don't really see any difference compared to one energy group. They're effectively identical, which is interesting. I was hoping to see some more interesting effects, maybe like an increase in accuracy, but we really don't see that. It's possible that this is just because we're using a very simple model and we might see differences once we use more complicated geometries and have more regions, but it doesn't really manifest in anything for this simple model. So what did we learn? Depletion calculations are very expensive. I highlighted that point a lot. Static energy discretized fluxes and cross sections yield low errors for abundant nuclides and moderate errors for trace nuclides with very low runtimes compared to transport dependent depletion. Oh, yeah, there we go. Yeah, it provides order of magnitude of speed up for low to moderate errors in nuclide concentration. And energy group structure does not seem to matter for simple models. Some gaps and potential places to expand on this work. Again, I already mentioned this, doing a more full core model with many different zones and materials would be interesting to see. Yeah, I can't really think of anything else other than that. These are all the people who helped with this work, all the funding streams and all the computing resources. And yeah, that's my talk. Thank you very much for coming.
Thank you so much. That was a wonderful start to the track. So remember that you can ask questions in the thread on Slack, in the track celebrating the Sci in SciPy Slack channel, and you can effectively upvote by putting emojis on the questions in thread. We'll start with a question from Matthew. Is OpenMC something that exists on PyPI or CondaForge? How do you and your collaborators install it?
That's a great question. OpenMC is not on PyPI because it has some other dependencies that make that difficult. It is on CondaForge, so you can install it via Conda. If you want to do anything parallel with it, you need to install it from source.
Thank you. From Kyle, the relative errors in actinide concentrations in case 2 seem to have a trend that grows. Does that represent some accumulation of error?
Yeah, I would say it is the error propagation from your assumption that the fluxes are static. So as time goes on, you're getting further and further away from your static flux assumption.
Good. So another one from Matthew that I will read. In my Software Research Institute for Physics, we like to focus on, quote, reducing the time to insight rather than just wall time of code execution. You showed timing for different cases, presumably with code that used Python bindings. Does having the Python bindings help users to reason with their conceptual modeling problems to make these timing periods faster in the human work wall time, or are things mostly being run through config files?
Can you read that again?
Do you want to try and rephrase?
So, like, can you mention how, if at all, the Python bindings are actually accelerating your human ability to get to ask the questions you want?
You mean like in the Python API?
Yeah.
Yeah. So I would say compared to other codes in this space, there is no uniform tool for those input files to be made and for their output to be processed. OpenMC is pretty unique in that ability. It has an API to programmatically generate its inputs, and you can also programmatically process outputs. So you can make plots like you normally would just in Python, processing that data all in Python. So yeah, I'd say it does speed up that process.
Thanks. Next from Lundy, are you able to verify the results of these simulations against real experimental data?
I haven't looked. It's possible.
Sounds expensive.
Yeah.
Great. Next from Joshua, do U.S. export controls impact how OpenMC can be shared or the capabilities that can be included in it?
That's a great question. To my knowledge, the answer is no. OpenMC is kind of a unique case in that it's a Monte Carlo code that's open source that has a lot of features in it that a lot of the export controlled Monte Carlo codes also have. Mm-hmm. Somehow they're able to be open source and get away with it. I don't know how they do it, but they do.
Very good. How mature is OpenMC relative to MCNP, which hopefully means something to you? Is OpenMC being used for commercial application? Is it part of a regulator, i.e. NRC approved methodologies? Well, I'm a soft condensed matter physicist, so I'm tripping over this. Does that work?
That's a really good question. MCNP is around 40 or 50 years old, and it uses a design philosophy that has sort of stayed the same from those very, very early days. It's very mature code, but it has a lot of legacy code in it. They're always trying to improve it. OpenMC, I think, was started in 2000. It was in the late 2000s or the early 2010s, so it's much less mature, but it has the benefit of more modern software development practices. Insofar as if it's used in the commercial space, yes, it is. I know there's a couple companies that are using it. I don't think anyone uses it for NRC licensing yet.
Got it. I'll use my moderator prerogative to inject a question. In that tech stack that you listed early on, HDF5,
Yep.
SciPy matrices, sparse matrices, et cetera, is there anything that you see in the tools plenary or as you look around that looks like it might solve a pain point or a friction point in your work? Like moving from HDF5 to one of the newer formats or to the new SciPy sparse, anything? Or is it such a mature workflow at this point that SciPy as it has been is good enough?
I think the tools right now are good enough. It really depends on sort of what funding is available and what projects people want to do with OpenMC. Like, I think they're always open to improving their code, but someone's got to get in there and actually do it. Mm-hmm. That's sort of the nature of having this open source code is the maintainers can only do so much, and they have a very sort of limited scope of what they're focused on.
Very good.
But if anyone's interested, I encourage you to contribute. It's a wonderful project.
Great. I'll read on the mic here, clarification from Deacon. OpenMC was originally developed under a basic research exemption for export control. And with one more question, and I think we'll leave it. Is the temperature density change significant enough that it needs to be included in the model?
If you're trying to get better results, yeah, you would need to couple to some sort of thermal physics code and then jump back and forth between your neutronics and your thermal physics. There's a code called Cardinal that does that, and that's also open source. You can go look that up. If you look up like Cardinal OpenMC, you should be able to find it.
All right.
Yeah.
Thank you for fielding all these questions, Oleg.
Yeah.
One more round of applause for Oleg to thank him.
Thanks for the questions, y'all.